In this video, you will learn how to generate random dungeon-like levels in JavaScript using what is known as a random walker algorithm. Now obviously the maps currently being generated are on the more basic side of things. That is because the focus of this tutorial is on the actual algorithm that gets randomly drawn to the screen. Cosmetics and game logic can be handled by yourself. There is already a wealth of information out there on the internet that explains these things. What is most important is getting you to understand how this algorithm works and how you can translate its values into graphics on the screen. That being said, it is worth mentioning that this tutorial is done using Html5 Canvas. Basic Canvas knowledge is therefore assumed, although we won't be doing anything too advanced, so don't worry. Here we are in a new project with the HTML boilerplate code already set up. The only thing that I've added to the body is this canvas element with an ID to give us easy access to it, and the script tag, which is where we will be spending the majority of our time in. Likewise, here is the styling for this markup. We have removed the overflow from the body because we will be setting the canvas to take up the entire width and height of the viewport. In some browsers such as Firefox, doing this can interfere with the body element sizing. This can lead to a scroll bar being added to the browser on either the X or the Y axis. We don't want this scroll bar, we want the user to be able to see the canvas and nothing else. Therefore, we set the overflow to hidden on the body, so that no matter what, users won't be able to see any scroll bar. As always with Canvas, we need to create a reference to it and extract its context before we can do anything else with it. We will then do what we said we would do earlier, that is set the canvas's dimensions to match the viewport's dimensions. This will make the canvas spread out over the surface area of the viewport. These values will be determined by the size of the client's viewport. We are splitting up their viewport into 1,000 rows and columns each. We do this so that we can get a unit of measurement that is dynamically linked to the unknown size of the client's viewport. Because columns go from top to bottom, we will use these to act as a kind of width value. Likewise, the rows will be the opposite and act as a height value. This function will be the repeatedly invoked function that will facilitate animation on the canvas through the rapid re-rendering of slightly altered graphics on the last frame to convey the illusion of movement. We wrap it in parentheses with curly braces at the end to call it on initial document load, or as soon as it is compiled. This way we don't have to call the function itself down below. To request animation frame, we use recursion and invoke the animate function in on itself. To prevent a stack overflow, it limits the speed at which the animate function can be invoked to 60 frames per second, an ideal speed for smooth feeling applications. Just to demonstrate that the dynamic cols and rows units do work, we will draw a rectangle that is 50 rows wide and 50 cols tall. It will be positioned in the exact center of the screen, which is why we have moved the X and Y offsets of the rectangle back by half of its width and height values respectively, even though the X and Y offsets are already set to be half of the relevant viewport dimension. If we didn't do this subtracting, then only the object's top left corner would be in the middle of the screen and not the actual object itself. As you can see, here's the object that we have drawn, and we can resize it, and yes, it's still in the center, and obviously it resizes itself based on the current viewport size. This is good. At the core of the random walker algorithm is a matrix. A matrix is a two-dimensional array, which means an array that contains arrays in and of themselves. Because of the way that arrays work, we access the horizontal and vertical positions a bit differently from how we would position a vertex when we use the standard Cartesian coordinate system. In this instance, the individual arrays listed inside of this parent array represent the individual rows of our 2D canvas. Inside of these arrays we have integers, either 0 or 1. These individual numbers represent an individual column listed in order inside of the specified row. You should now be beginning to understand how this 2D matrix works. It is essentially just an elaborate display of numbers that can represent real 2D space on our canvas to which you can draw our graphics onto. This function will automatically generate a 2D matrix for us. Useful because making one ourselves with the number of rows and columns needed would be a very time-consuming and inefficient process. The num parameter is the value that we want to fill our matrix with. These last two parameters allow us to customize the number of rows and columns that our matrix has. This is helpful because generally computer screens are not square in nature, they are some sort of rectangle. Therefore, it would be disproportionate to let our matrix have the same number of rows as columns because we want our matrix to represent our entire viewport and not some isolated square inside of it. The only proviso is that we have the same number of columns within each and every row in the matrix. This outer loop will push the number of rows that we need to the parent array. Remember, the rows are represented as individual arrays within the parent array, hence why we are doing what we are doing here. We need to push the same amount of numbers to each row. These numbers will act as the individual columns within a row. To do this, we create a nested loop within the rows loop. It will loop through the number of cols that we configured with our parameter and push the same numbers to each row as soon as the row itself has been created and pushed to the parent array. And finally, of course, we return the matrix that we have just created. Now, having our matrix generation function is all well and good, but if we don't use it, then it is ultimately useless. To use it, we first need to determine how many rows and columns we want our matrix to have. We could just use 1,000 for each because that is where we got our original row and column values from. This would not be wise, however, because if we did, then our matrix would be far too large. 1,000 rows with 1,000 columns means 10,000 individual items within that matrix. This operation would take up far too much processing power for its own good and would make it impractical to work with. To get values that are both representational of the current viewport dimensions and also streamlined, we multiply the division of the canvas's width or height with either the size of a row or a column depending on which canvas axis we are working with. We then multiply the final value by 85, which is an arbitrary value chosen through trial and error simply because it looks good in most cases. Keep in mind that you can change this value if you don't like the look of what is generated. Now, these values here do not relate to the matrix's graphical representation on our canvas. To translate the matrix's numerical data into canvas material, we divide the matching matrix column or row number with either the canvas's width or height, so that the matrix can match up with the canvas's dimensions to make a tight fit. So this is it then. This function will contain our random walker algorithm. Just don't get trepidatious, I will explain everything as I go along. Again, you can tweak these values to your choosing. They both configure important characteristics that every randomly generated map will retain. In our case, we want our entire path to have no more than 15 turns, and we want our path to make no more than 10 steps in a single direction, without changing direction to a direction that's perpendicular to the current direction. This map variable will therefore hold the matrix. Our path will start in a random position on the matrix. These two variables will hold that starting row and col position. The random number generated will be one less than the path height or path width, depending on which one is being used. This is because math.floor always rounds down. This is fine because arrays are zero indexed, meaning the values generated will be relevant to our matrix. This array holds the possible directions of travel. We can't go diagonally, we are only able to go up, down, left and right. We list these characteristics in that order inside of this array. They are represented as such because of the characteristics of our matrix, where the rows are accessed before the columns within the rows. Therefore, -1 means that we go up to the preceding row. The accompanying 0 means that we don't move at all column-wise. Therefore, in the first item, we go up a row. The whole point of our algorithm is its random nature. The first variable will hold the new direction of the path. It is an array because it will hold an item from the directions array that we have just created. The second variable will hold the previous direction of the path so that we can travel in a new direction. It is currently empty because we are not travelling in any direction at the moment. Our path will run for either as long as max wars has not depleted its value to 0, or until the path tries to travel outside of the size constraints of its matrix. We will begin travelling in a random direction as specified by the directions array previously created. We will keep on generating a random direction until the direction returned is either not the same as the direction that we are already going in beforehand, or the complete reverse of the direction that we were already going in, meaning that the path would just backtrack over itself. We use math.ceil to round our random number upwards. This means that the number returned will be between 1 and our max length variable. The war length variable will serve as an iterator so that we will be able to tell if our path has exceeded its max length or not. This is how long this loop will run for. As said before, we need to end the path if the algorithm tries to go outside of its matrix boundaries. All of the possible scenarios where this could happen are covered in this if section. For example, here, We are currently on the top row and are trying to go upwards into a non-existent row as we are already on the topmost row. If we are still travelling within our matrix though, then we will change the associated position on the matrix from 1 to 0. Doing this is key. When rendering outer graphics onto the canvas, we will separate the zeros from the ones. We will know that the zeros are where our path should be and the ones are where our stage boundaries should be. If we are still travelling within our matrix though, then we will change the associated position on the matrix from 1 to 0. Doing this is key. When rendering outer graphics onto the canvas, we will separate the zeros from the ones. We can use this to determine where our path and stage boundaries should be, because the zeros are where our path should be and the ones are where our stage boundaries should be. Alongside this, we will also update the current row and current col values with the correct direction values that we were just travelling in, and increment the wall length so that we know how many times the path has travelled in the same direction. If we have reached this point after the nested while loop, then we will know that the algorithm hasn't collided with the matrix's boundaries. If it did, then we would have exited out of the loop with the break statement. If this is the case, then we will update our last direction with the direction that we have finished travelling in. Then we will decrement the max wars variable, so that the parent while loop can have a base case and not run forever. Finally, outside of the parent while loop and just before the function ends, we will return the map variable, altered from its original form of just ones. It should now have some zeros which will represent where the path has just been. We will test this out to see if it works properly. So we'll log it to the console and then we will see. So here we have an array, and as you can see there are zeros present as well as the ones. And we'll refresh. Okay, it actually changed because this inspector is actually decreasing the size of the viewport. If we do it again, yeah, as you can see now it's only 2 arrays now, only 2 rows, because look how short it is. But then if we expand it out, again it goes back to 5. So this is all working fine. And as you can see, the zeros and ones, they change position each time. So here we have, a lot of ones on the first 2 rows. But then now, or actually all of them start with ones now, so there's a lot more. So as you can see, this is random. As for how we are going to get this capricious matrix drawn onto the canvas, that is a whole new challenge in itself. We are going to do it by extracting the non-path values from the matrix and rendering those as black rectangles onto the canvas. So as a consequence, the path will just be anything that isn't a black rectangle in the canvas. By default, the path will be white because that is the default colour of an empty HTML document. This may seem counterintuitive, but in an actual video game, we would want collision detection on these barriers that encapsulate our path to prevent the player-controlled object from straying outside of the path. This function works in a similar vein to the create2d-array function which we used to create the initial matrix. Like before, it employs a nested loop so that each column of every row can be accessed in turn. When it does access an individual item from the matrix, it checks to see if its value matches the value of the val parameter, which you can configure ourselves to the exact value that we want. In our case, that will be 1 because we want everything that isn't a path, and a path in the matrix is currently set to be represented by 0. So if the item does match the val parameter, then you'll push its x and y values or what column and row values it is on as an object to an array that will be returned by the function. Because 1 is our val parameter, we know that the values returned will not be a path, which is represented by 0 in our matrix. This function will be called in the animate function. It will draw out the barriers forming a path as a natural consequence. Instead, we will loop through each and every object in the array, ensure that they will definitely be painted as black, and then finally draw the point onto the canvas with the width and height values that we defined a long time ago. These width and height values will also be used on the positioning of the rectangle. Without it, the boundaries wouldn't be positioned correctly. So we will replace this code with the drawMap function. As you can see, things are not looking as good as they should be. There is a very obvious gap between the boundaries that should be rock solid. Furthermore, the way that we are rendering these boundaries onto the canvas isn't very efficient at all. We are rendering them out as individual items onto the canvas, which is wasteful because for a lot of the time, the rectangles are not isolated on their own. They are part of an even greater polygon. It would make more sense if we grouped the boundaries into as many different rectangles as we could. instead of rendering out each rectangle individually, which is both resource intensive and isn't the nicest to look at. This function will do just that. It will take in the array of points that we are currently looping through. The array that it will return will be a lot faster than the one that we are currently using. At the moment, the coordinates inside of the array are not ordered in any particular way. It is our job to solve this. The first loop groups the coordinates by their rows. This filter method returns an array in itself. The array returned will contain all of the coordinates with the matching y value or column that is currently being looped through. We loop through the past height value to get access to the number of columns in the matrix. As for grouping by rows, that is a bit trickier. Essentially, we are going to congeal all of the columns on a row into one until we reach a point where there is a gap in the row between the columns. So until there is at least one missing column in a perfect sequence of add 1 to the previous value. We have y value as a second index in this loop, because currently y group is an array containing arrays. Each array represents a new row starting at 0. Therefore, whatever array we are currently looping through, its row in the matrix will be represented by this y value parameter. As for separate x, that will be an array of singular values. The values in question will be the x coordinates on their own from the array of objects held in the group iterator. We need this array because we are going to create a function that will insert null into our array on all points where there is at least one missing column in the sequence of joined together rectangles. This will be that function. We will loop through the array as normal. If the item in the array currently being looped through is not one less than the item next along in the array, then we know that a null value will need to be inserted between the current item and the item next along, because there is a discrepancy in the sequence that should be increasing by one at a time. The only exception to this is if we are at the end or beginning of the array. That is what this if statement checks for. A null value will only be inserted if there are actually two items to squeeze a null value in between of. The splice method used on the array of our choice is saying insert null next to the current item without moving the item that used to be in null's place. Instead, it will be pushed towards the right. This will be assigned to many different arrays throughout the loop, which we are about to create. Each array will be represented as a seamless rectangle without any breaks. Every time it is assigned a new array, it will be pushed to the already created split array. It won't be assigned an array value until we reach a point in the modified array where there is an actual number being returned and not null. If we have reached a number, then it will now become an array, which as promised is pushed to the split array. When this happens, we will push the number, which we know that we are on because it is not null, to the array that is now held inside of the split array. We do this for all subsequent numbers until another null is met in the sequence, in which case sequence array will go back to being null until another number is met, whereby it can go back to being an array that will now be adjacent to the previous array in the split array. This cycle will repeat ad infinitum until the entire array has been looped through. Of course, we wouldn't have done all this work if we weren't going to return a value at the end. So going back to the original condensed path function. We must first sort our array of x coordinates into ascending order. That is the proper formatting required for our split array missing val function to work as intended. Now we can utilize that function. Since split x will now be an array within an array, we can loop through the individual arrays held inside, and for each we will push an object to a new array. The objects in question will contain the starting x coordinates of the glued together rectangle, the length of it, or the number of rectangles that its width runs for, and the row that it is on or its y coordinate. X group is our final formatting and will therefore be our return value. Actually, I forgot to include the x group, but it's just an empty array. We can now use all of that formatting on barriers so that its value will be something more lightweight and practical for us to work with. Finally, we will need to adapt the rectangles that we are drawing to the canvas to reflect this length parameter. Otherwise, each rectangle would just be the width of a single rectangle, when in actuality it may be multiple rectangles on the same row stuck together to make one long rectangle. And so here we have it. This is the random dungeon, and as you can see it looks a lot better now, and it's also more efficient. As you can see, there's no gaps between the blocks, everything's looking good. And we can keep on refreshing and see all the interesting designs that it will create. I mean, I don't know how many different combinations there are, but it would definitely be a lot. Too much for the user to be able to just see them more through refreshing a couple of times. So that's pretty much it for this one, guys. I hope you understood what was going on here. I know that this was a pretty involved video with a lot of complex logic going on contemporaneously, so props to you if you understood it all. If not, don't worry, you are free to ask me for clarification anytime you want down in the comments box below. I would be more than obliged to answer any of your requests. Anyway, that's all from me. Peace out and have a great day.